Okay, now we'll continue with some more design of T-beams. Lecture 21. Now, as I mentioned in the morning, how the load distribution happens in case of one-way slab, and yesterday I also discussed about how the load distribution happens in two-way slab also. Now, in the one-way slab, for an intermediate beams, this is an intermediate beam. Intermediate beam is a one which has slab on both sides, both of its sides. Okay, so this is an intermediate beam which has a slab on left and right side. Similarly, this is also intermediate beam, right? So now this becomes the span of the beam. This 8 meters become the span of the beam, and the beam is resting on, let us say, this brick wall, and this is another brick wall. Okay, now the center to center distance of all the beams are 4 meters. So the effect of the this beam will carry load from the slab to the same center to center distance 4 meters only. Okay. Now, if I want to remember, as I told you, the load on the slab will always be expressed. Load on the slab that total load will be always in terms of so many kilonewton per meter square. It is a aerial load. Okay, so many kilonewton per meter square. Now, how this load will be transferred from the beam? Remember, when you say a slab, only slab alone doesn't exist, because obviously you are designing a structure for a people to occupy so that it can be put into use. So any floor or roof, it is not left unfinished. On top of the floor and on top of the concrete slab, you also have some sort of finishing. It may be tiles, it may be marbles, it may be granite, it may be simple cement flooring. There are varieties of flooring that you can go for. Okay, so now how to calculate the load on the beam, on this intermediate beam? So this is what this black color is, the one is the beam. That beam is this one. This beam is the one. Now now I want to calculate on this beam what is the UDL intensity, that is kilonewton per meter. Right now the beam is supporting the slab, like if I show here 1 second. So if you take 1 meter length of beam, I am taking only 1 meter length of beam should withstand load from this much area up from slab. Okay, if you take only 1 meter length of the beam, this 1 meter length of the beam should always take the load from the entire area. So let us say this is the WU is the so many kilonewton per meter square. So WU into 1 into 4 will give me total load on the slab on this area. Okay, that will act as a UDL on the beam, like this light. And that now here on the beam it will become so many kilonewton, because WU is in kilonewton per meter square. Kilonewton per meter square into 1 meter into 4 meter will become 4 WU kilonewton. So 4 WU kilonewton per 1 meter length of the beam. Same way, if you can take another 1 meter, then it will become another same intensity. Likewise, we calculate like this. This is also same intensity. Next 1 meter also same intensity. Next 1 meter also same. Likewise, we will calculate for. You remember, either the beam or slab, we always design for 1 meter length, and the same thing we will adopt. Okay, so now here, you see here. Now I have shown only 1 meter length, 1 meter here, 1 meter length of the slab, which is being supported on the beam. Now this is 4 meters. Now if you take a cross section here, this is a beam. This is a beam visible rectangular visible to you, and this is a slab, and top of that there will be a floor finish. Okay. Now this 1 meter, how much load it can take, that's what we discussed. For example, if we have, this is the 3D view. If you cut that beam, you have this rectangular, this is a slab. On top of the slab, we have a floor finish. So if you take 1 meter length of, if you take this 1 meter length of, if you take this 1 meter length of the beam, this beam has to carry, there will be some live load here. Okay, there will be some live load. So the slab will have a live load, and it has a, this is called floor finish. So the slab has a floor finish, and this is the slab itself. This is the self weight of slab or dead load of slab. Self weight of slab is there, right? All these three things will be acting on this beam. So this beam itself will have a self weight of beam. So when you finally design, you will take into account of live load, floor finish, self weight of slab, self weight of beam, and finally when you are designing a beam, your load will be so many kilonewton per meter, like this. If there are only UDL is there, you will UDL intensity on the beam is so many kilonewton per meter. Okay. While solving the example, you will understand better. So we will directly go into the problem. Let us say if you take 1 meter, all this 1 meter, whatever there, everything will come to the beam. You have to design it. Okay. So for example, let us say we take a problem. And by the way, this kind of question will be asked for 24 marks. You read the problem carefully. A hall of internal dimension, make a note of it, internal dimensions 5 meter by 15 meter has beams spaced at 3 meter center to center and a slab of 125 millimeter thick. Okay, so the inner size of the hall is 5 meter by 15 meter. And it has a beams spaced at 3 meter center to center, and it has a slab of 125 millimeter thick. The beams are supported by walls around 300 mm thick. So the beams are resting on the brick wall of 300 mm thick. The superimposed load and live load are one and the same for all practical purposes. The superimposed load on the slab is 5 kilonewton per meter square. Please note down the unit, kilonewton per meter square. Design on intermediate T-beam for flexure and shear. The shear topic will come in the next unit, so that's why it is marked in red. So right now we will design only for a flexure. Flexure means bending moment, maximum bending moment, or a factored bending moment we will design. So design the intermediate T-beam for flexure and shear. Use M30 grade of concrete and Fe415 steel. Do the necessary checks. Draw to a scale longitudinal section and cross section of the beam showing the reinforcement details. So like this only in your end semester examination you will get a question. It will be of 24 marks and you have to draw to a scale longitudinal section and cross section. So this longitudinal section and this shear design for shear we will see in the next class. Next class means the next unit. Okay. So right now we will take up this same problem while doing the shear design. So right now we are going to do only design of intermediate T-beam for flexure alone. Okay. Right now, right. So now you see the given data. This is the hall where this internal dimension is 5 meter. From inside of this to this end is 15 meters. This is a brick wall all around. This is in plan. This is a brick wall all around. And that all around brick wall thickness 300 mm thick. Now, as I mentioned in the yesterday's class, and you also rightly said, how will you orient the beam? Here they are saying that the beam, it has a beam spaced at 3 meter center to center. So obviously your beams will be from this center to next center. This is one beam. another beam, another 3 meter, in another next 3 meter another beam is there, in next 3 meter another beam is there. So you have 3, 6, 9, 12, 15. Total center to center is 15 meters. Now to provide slab, you have to provide a beam at every 3 meters. So 3 meters center to center. After this will be covered with slab. Okay. So now if you take a cross section here, this is a brick wall. This is one beam, this is another beam, this is another beam, this is another beam, this is another support, this is a slab, and on top of that there will be a floor finish will be there. So these are all the given data with respect to the room. Now in addition, you also have a thickness of slab. The thickness of this slab is given as 125 millimeters. That is here DF as per our sign convention. Now the beams are supported by walls around 300 mm, which I already told you. The superimposed width of the wall is 300 mm. That's what I have written here. Clear span of the beam. This will be okay, because you are spanning your beam is like this. The clear span means from face to face of the support, from here to, sorry, not in this one, in the floor plan. Inner dimension is only 5 meter. So that is a clear span of the beam, that is 5 meters. 1 second, I'll just go back. Clear span means from this face to this face, the inside dimension, that is called clear span of the beam. Okay. And that the clear span means what?
Yes, sir.
Okay. DF is 125 millimeters. Width of the wall all around, that is 300 mm brickwork. Clear span is 5 meters. Remember, span is 5 meter, not 15 meter, because if you provide a 15 meter long span, the depth of the beam will come around 2 meters. So you should not have 15 meter span and all. So clear span will be 5 meters. Live load or superimposed load is given as 5 kilonewton per meter square, and FCK is given as 30 MPa. FY is given as 415 MPa. Okay. Any doubt in this, anyone so far? Anybody have any doubt?
No, sir.
Okay. Right now, you see, they have not given what is the depth of the beam, what is the width of the web, what is the depth of the, nothing is given. You have to design. So what to do is, because now is the beam is this, each and every beam is a simply supported beam or a fixed beam? The each and every beam that we are going to design, one intermediate beam we are going to design, that beam is a simply supported beam or a fixed beam? The beam is resting on brick wall, or it is resting on some column or something like that?
Brick wall.
So the beam is resting on the brick wall. That means, is it simply supported beam or a fixed beam? Simply supported beam. That's why. Yeah. So here the beams are supported by walls. That is brick walls. Walls are usually brick walls. So the beams are supported by walls around means it is a simply supported beam. Okay. So Jagradiga Minandi, supported by walls around. Okay. So now we have to decide the cross-sectional dimension. So what we will do is, you know, from the code book here in 23 point something, 1 second. See here, for a simply supported beam, this is for a simply supported beam, the span to effective depth ratio has to be 20. This is the maximum value. You cannot go beyond 20. Okay. For a simply supported beam, the span to effective depth ratio up to span 10 meter is 20. So this we are going to take as a reference. So here, as per class 23.2.1, A for a simply supported beam, effective span by D maximum value is 20. So what we are going to assume? I am going to assume 15. You can assume any value less than 20. It does not matter what value you assume, but the value should not be greater than 20. Okay, L effective by D maximum value is 20 is given in the code as per this class. So I am taking L effective by D as 15. Now for a simply supported beam, how do you find the effective span? For a simply supported beam, clear span is given and the width of the support is given. So how will you find the effective span?
L plus D, sir.
L plus D, that is one criteria. Equity?
L plus
Clear span
W
plus
center to center.
L
Clear span plus?
effective depth.
That is clear span plus effective depth.
Clear span
plus width of the
standard
support,
to
right?
Center to
the
center.
walls.
Either center to center of support or clear span plus width of support. Both are same, right? So because right now I don't know the value of D. Right now I do not know the value of D. So but I know the only other one. L effective is equal to clear span plus a width of the support. Actually it should be center to center of support or clear span plus width of support, also same thing. So 5 plus 0.3, 5 meter is the clear span, 300 mm is the width of the support. So 5 plus 0.3, 5.3 meter is the effective span. Now using that I am going to find out what is my D value. So L effective by D is equal to 5300 by D is equal to 15. So if you put 15 here, you will get D as 354 millimeters. Okay, so for the safer side, I have made D as a 400 mm. Okay, so if I put 400 mm here, 5300 by 400, obviously this will be much less than 15. Okay, you can choose 360, you can choose 355 also. Anything is fine, but this value should be more than this. So that is why I am telling you, design is completely a independent problem. Every person will get a different answer. So I have evaluated D as 354 mm, but I am going to provide D as 400 mm to be on safer side. Okay. Now, therefore, this is only effective depth. This is only effective depth. So overall depth will be effective depth plus diameter of the main bar by 2 plus stirrups diameter plus clear cover. Okay, and this you already know. So as I am assuming the main steel as 20 mm diameter and stirrups dia as 8 mm. So I will get effective depth is 400 mm, which is coming from here. I am assuming 20 mm dia bar as the main bar. So 20 by 2 is 10. I am assuming stirrups dia as 8 mm. Clear cover is 30 mm. I am assuming. See, minimum, if you see the code table 16, it says 20, 25, 30 and all these things. So I have taken here 30. Okay, for a severe exposure areas, it is 30 mm. So together it is coming out to be 448 mm. Obviously, nowhere in the world they will provide 448 mm as a overall depth. So it will be, you can make it as a whole number 450 mm. So these are all, everything is approximated only, but it should be within the limit. That is the only point. So you need not have, sir, it is coming 448.23, why you are putting 450 mm? That is absolutely not necessary. Whatever value come, you can round it up. Okay, D is equal to, ideally if you calculate is 410, 418, 448 only. But a laborer cannot do 448 mm exactly. But 450 mm we can easily do it because that is 1.5 feet. So 450 mm I have provided overall depth. Any doubt to anybody so far?
No, sir.
Those who have doubt, you can ask.
No, sir.
Okay. So now, width of the web. See, while discussing the rectangular beam, I told your one criteria was your depth of the beam should be 1.5 times to 2 times the width. That's what we have desired. We have I told you this was one of the specification. Your depth should be 1.5 times to 2 times the width. So here I am taking, let us say t is equal to 1.5 times b. So b will be d by 1.5, that is 450 divided by 1.5, which is equal to 300 mm. That's what I have taken here. Assume the width of the web as 300 mm. Okay, this is not arbitrary. This I assumed from here. Overall depth of the beam is equal to, it should vary from 1.5 to twice the width. So I am taking d is equal to 1.5 times b, and from this I got 300 mm, right? I remember that this beam width should not be greater than the width of the support. Suppose if your brick wall width is only 230 mm, then you cannot have a width of the beam more than 230 mm. Please be clear. Width of beam cannot be greater than width of the support. It can be less or it can be equal, but it cannot be greater than the width of the support. That is the only thing you should keep in mind. Okay. That is the only thing you should keep in mind. So if you ask me how 300 came, that is from here, and that is within this width of the support. Actually, it is equal to the width of the support. So it should not be greater than the width of the support. Okay. Okay. So this is a cross. Now I got cross sectional dimension. My width of the web is this much. My overall depth is this much. My effective depth is this much. Right. Now, what will be the next step? One thing is missing here. Like this is my T beam. I will assume this value. This slab thickness is given in the problem itself, 125. Effective depth I have already found out. Overall depth also found out. What is missing here? Anybody tell me?
Flange.
Effective width of the flange.
Effective width of the flange.
So this is not that you have to find out, right? That will be your next step. So now for T beam, effective width of the flange is equal to L0 by 6 plus BW plus 6 times DF. Once again, I will remind you, all the parameters should have the same unit. So L0 is for a simply supported beam, effective span itself will become a L0. So 5.3 meters is 5,300 by 6. BW we have assumed that to be 300 plus 6 times DF. DF is given as 120 mm, 125 mm thickness of the flange or thickness of slab in the problem itself. So if you find that is coming out to be BF is coming out to be 1933.33 millimeters, and the actual width of flange is how much? 3000. How this 3000 came? Remember, you had a 5 meter by 15 meter room, 15 meter room, and the center to center of each beam is 3 meters. So obviously, this each one is 3 meter. Okay, each center to center is 3 meter. So if you consider this beam 1.5 meter from this side, 1.5 meter from this side, that is your actual B. Actual B is this. That is 3 meter. So actual width of flange is center to center of beam itself will become actual width of the flange. So that is 3000. So you can take BF as 1933.33. ఇది అందరికీ అర్థమైందా? ఇంకోసారి చెప్పాలనా? వినట్లేదు. I could not hear. Somebody said something. Okay.
Yes, sir. Yes.
Okay. So fine. Very good. So now I have already calculated all the cross-sectional dimension. BF is there, Effective depth is there. Thickness of flange is given. Overall depth is found. Overall depth is necessary for finding out the self weight of the beam. Okay, and width of the web also known. Okay. Now loads and bending moment, that is the next step. Now remember, this is my 400 mm is the effective depth. I will take laser count. 400 mm is the effective depth. 1933.33, you can make it to 1933 for ease of calculation. 1933 is the flange width, effective width of flange. 300 mm is the width of the web. 125 mm is the slab thickness or the flange thickness or depth of flange whatsoever. AST we have to find out. Okay. Now this is the cross section of the beam. Now on this slab, live load on the slab is given as 5 kN per meter square. Okay. In the problem, the floor finish is not given. You should always account for floor finish also. Before that, I will add the self weight of the slab is, remember, if for a slab, if you want to find out self weight, I have told you this morning also, you will always calculate for this one. I don't know whether I have here. Yes, here. See, this is 1 meter length. This is 1 meter length. This is 1 meter width, and thickness of the slab is 125 mm. So you calculate for 1 meter by 1 meter by 0.125 meter. That is this 0.125 multiplied by the weight density. In general, we don't write this one. Okay. So if you want to find out the self weight of slab in terms of kilonewton per meter square, it is simply nothing but thickness of the slab in meters multiplied by weight density of RCC 25. This is in meter. This is in kilonewton per meter cube. So self weight of slab will be 3.125 kilonewton per meter square. Why I am working out in terms of kilonewton per meter square? Because live load will always be given in terms of kilonewton per. If you take in your floor, if you take 1 meter by 1 meter, at any point of time, the number of people, any moving equipments, all these things, the total weight will be only 5 kilonewton per meter square maximum. In 1 meter by 1 meter area, the live load can be only 5 kilonewton per meter square. Similarly, I am calculating self weight of a slab for 1 meter by 1 meter. That is coming out to be 0.125 into 25, that is 3.125 kilonewton per meter square. Now, what is left is there will be a floor finish here. Some finishing will be the flooring will be there. In the problem it is not given, so I have to add it. How? Normally it is taken as 1 kilonewton per meter square. Floor finish is taken as 1 kilonewton per meter square normally, but you can take a value suitable to you. For example, here I have this is 5, this is 3.125, and I want to make it a whole number including the floor finish. So what I am doing is I am taking floor finish as 0.875, so that I will add this 0.125, 0.875, 0.875 will become 1. Is that clear? So either you can take 1, or if you want to make this whole number, I will take the appropriate value. So if you calculate all these things, this is coming out to be 9 kilonewton per meter square. So here in this sphere, if you see, up to here we have finished. This is the live load. Here live moving equipment, some vehicle is moving here. Small, okay. That is the live load we have found out to be 5 kilonewton per meter square. Okay. Now this red part is a floor finish. So floor finish we have taken 0.875. Now this slab weight for meter square we have found to be 3.125 kilonewton per meter square. So together we got 9 kilonewton per meter square. So okay, so that's what we have done so far. Now, okay. Obviously, the slab will cover entire room. Okay, slab will be covering the entire room. Now, if you take any intermediate beam, let us say I am taking this intermediate beam. Now, this intermediate beam, half of the slab load will come to this intermediate beam, and half of this will come to this intermediate beam. Okay, is that clear? Okay, so ideally, if you see here, this ideally the single panel is coming out to be 5/3 is less than 2. Actually, the distribution will not be like this. Either the spacing should have been 2.5 meter, or this span should have been more than 5. Okay. So, but it's okay. You can assume that this is a distribution. Now, see here. This is 3 meter. So half of means 1.5 meter. From this beam to this beam is 3 meter. Half of them will come to one beam. So it is also 1.5. So together it will become 3 meters. Okay. So now this is becoming 3 meters. So now for 1 meter width of 1 meter length of the beam, in the 1 meter length, how much load will come? This 9 kilonewton per meter square is the total load on the slab, including the self-weight, including the floor finish, live load. So load on the beam, load transferred from slab is 3 meter. That's what this one. This is 3 meter. This is 1 meter. So 3 meter into 1 meter is the total area in this portion, and all this load will act on the 1 meter length of the beam. So 3 meter into 1 meter multiplied by 9 kilonewton per meter square. That's what I have written here. 3 meter into 1 meter into 9 kilonewton per meter square. Or you can simply say, let us say this W is 9 kilonewton per meter square. Remember, these are all service load only. Because given load was also service load, there is nowhere factor load is mentioned. That is why I am writing W. I am not writing WU. So W is equal to 9 kilonewton per meter square. So here load transfer from slab to the beam is W multiplied by center to center of beam distance. So 9 multiplied by 3, that is 27 kilonewton per meter length of the beam. Okay, this is the, for 1 meter length 27 kilonewton will be acting on the beam. Idi andarku ardhamainda? Anybody having any doubt? Now, if you don't have any doubt, I will further proceed, or I will explain. You can tell me if you have not understood.
Sir, explain floor finish, sir.
Floor finish. Okay, see,
Yes,
if floor finish is not given, you can take 1 kilonewton per meter square. I can easily take this as 1 kilonewton per meter square. Simply assume floor finish as 1 kilonewton per meter square. Then I will have how much I will have? 9.125 kilonewton per meter square. I do not want this 0.125, that's why I have taken 0.87 to make it as a 9, that's all. But if you want, you can take as 1 kilonewton per meter square, and then you add all this thing, 5 plus 3.125 plus 1 kilonewton per meter square. Together it is 9.125, it will come. So in this here also 3 into 9.125 will come. It will be 27.375. That's all. Arthamainda?
Okay, sir.
Okay. So remember, we have done only up to the slab. This is, if I take here, I have included the floor finish. I have taken the live load. I can take the dead weight of a slab. What is left is this portion is left. This dead weight of beam is left. Okay. The dead weight of beam I have not included. That you have calculate per meter length. So self weight of the web portion. Web portion is, see here, what we get is what this is 125. This is 125 slab. This together it is total depth is 450, I think. This together, this total depth is overall depth is 450. This slab we already accounted for. Okay. So what is this height? This total is 450 overall depth minus 125. What 125 is the slab thickness. So web portion, what is the height? 450 minus 125, 325 mm. And the width of the web is 300 mm, we assume. Okay. So if you want to find out the self weight of the web, you should always see 25 multiplied by the cross sectional area, that is 0.3 into 0.325. That's what written in a different form here. 0.3 is the width of the web. 0.45 minus 0.125, that is this one, 0.325 multiplied by 25. Then I will get, if you want, you can multiply by 1 meter length we are considering. If you want, you can consider multiply by 1, or you can leave it as it is. So it is coming to be 2.4375 kilonewton per meter length of the beam. So therefore, any doubt in this one, self weight of the web or self weight of the beam portion, in this web portion alone? It is pretty simple. Just to take 1 meter length multiplied by the height multiplied by the width, all in terms of meter, multiplied by the weight density will give you so many kilonewton, and that you are finding only for 1 meter length of the beam. Okay. So this is the self weight of the web. That's all. Then you add everything together. So therefore, total UDN on the beam is 27 plus 2.4375, 29.4375 kilonewton per meter. For the sake of easiness, I am taking this as to be 30 kilonewton per meter. I can assume this one, there is no harm. You cannot reduce to 29, but you can always have a higher number. Okay. The final value should be rounded up to a higher number when you calculate the UDL on the beam. Remember, I have written only small w. So total factored UDL on the beam WU is equal to 1.5 into W, that is 45 kilonewton per meter. So maximum bending moment in the beam, you know, for a simply supported beam, maximum bending moment is WL square by 8. Instead of W, you should have a WU. Instead of L, you should have a L effective. So 45 kilonewton per meter is a W. L effective you already found out 5.3 square by 8. So remember, center to center of support was 5.3 meter. L plus D, that is 5 plus D is 0.4, 5.4. So we have taken 5.3. That was correct only. Okay. Your these are the two cases. 5 center to center of support is 5.3. L plus small d is 5.4. Least of this is 5.3. That's what we have taken in our earlier also, here also. That is coming out to be 158 kilonewton meters. This should be superscript 158 into 10 power 6 Newton millimeters. Okay. So there is this is 10 power 6. 158 into 10 power 6 Newton millimeters. Okay. Now, so far you have been given this value directly. In the last 3 problems that we solved, this bending moment value was given directly to you, but here you have to find out, and most of the time in the exam you will get this kind of question. Okay. So once this one is found, everything else will remain same. So next is what? Design of reinforcements. Actually, you can find out, if you want, you can first find out whether it is singly reinforced or doubly reinforced, because this is very less. This is coming to be only 158. 158 is very less value. So that is why I am directly finding out. If you want, you find out MUR limit. That will be in close to 600, 700 kilonewton meter and all. So I left it here. If you want, you can do that also. Then design of reinforcement. For that, you need to know, assume neutral axis lies within the flange. So this this and all like same wise whatever did in the morning. M is equal to 0.36 FCK XU BF D minus 0.40 XU. So you take all this thing on the other side, you will get this kind of equation where XU is coming out to be only 19.31 mm, which is the thickness of flange is 125 millimeters. So obviously your XU is within the flange. So our assumption is correct. So next, MER is equal to 0.87 FAST minus point. Either you use this equation to find out AST, or you use C is equal to T, that is 0.36 FCK XU BF is equal to 0.87 FY into AST. So XU just now you found out, PF everything known, you can find out AST, or if you use this equation also, you can easily find out AST because now XU is already found. Okay, both will give the same result, almost same result it will give. So it is coming out to be 1117 millimeter square as the area of steel required. So now if you see here, here is my table. If I put 2 number of this one, I will only get 982, right? So if I put 3 number of this one, I can get almost equivalent, I think. So I am going with 3 numbers of 22 mm. So 3 into 380, 1140. Only I am providing 23 millimeter square extra. This is the most optimal number of reinforcement that I can provide for this AST. Okay. So you have to, you should remember this one, because this will, if you remember this one, this will come very handy. It is very easy to find out number of steel. Okay. So provide 3 number of 20 mm diameter bars, that is 3 into 380, 1140 millimeter square. Any doubts so far? Okay. So percentage of tensile reinforcement provided is 100 AST provided divided by BW into D. 100 into 1140 divided by BW is 300. Effective depth is 400. So I have provided 0.95% tensile reinforcement. Why this is needed? This is needed for check. So check for AST minimum. You know this formula. This actually almost comes close to 300 or something like 300 or less. So 246 AST minimum. We have provided 1140. Always it is more than AST minimum. That's fine. AST max is 0.04 times PW into D. That is coming out to be 5400. So we have provided 1140. This 1140 is greater than 246, less than 5400. So your AST provided is greater than AST minimum, less than AST max. Your check is fine, perfectly okay. Next, you have to do the checks for spacing of reinforcement, which I have discussed many times. So spacing, how will you check? This is 300 mm. Two side cover is 30 mm, 30 into 2, and 2 stirrups will be there. Stirrups will be one stirrups will come here, another stirrups will come here. That is 2 into 8. Now 3 number of 22 mm rod is put, 3 into 22 divided by number of spacing will be number of bars minus 1. So 3 minus 1, 2. So you are getting 79 mm, right? SH minimum you already know, greater of diameter of the bar or 25 mm. So greater value is 25 mm. So your SH provided is more than SH minimum. That is fine. And SH maximum from table 15 for 0% reinforcement for Fe415 steel 180 mm. This and all we have discussed many times before. So you go back and refer. So SH provided is greater than SH minimum, less than SH max. So therefore this check is also okay. So this check has to be done in all the design that we did in the morning also. Okay. So this is check for spacing. Already AST minimum check is over, AST maximum check is over. Now spacing of reinforcement check is over. Next, check for deflection. Now please pay very careful attention. Now in the check for deflection, this L effective, that this is the actual L effective by D provided, should always be less than the allowable L by D ratio. These things. Okay. Now, what is this L effective by D for a simply supported beam? Basic value is 20. Alpha is span factor. If the span is more than 10 meter, but our span is only 5 meter, 5.3 meter, so it is only 1. Beta is depending upon the tensile reinforcement, amount of tensile reinforcement provided, and the grade of steel. So that we have to find out from figure 4. Gamma is for a compression steel. Here it will not be required because we are not providing any compression steel, because your MU will be much less than MU limit. So it is only a singly reinforced section. There is no compression steel. So for that one, but zeta will be there because it is a T beam we are designing. So modification factor for flanged beam we have to find out. Okay. So this one I want to elaborate little bit further. So modification factor for tensile steel from figure 4 of IS 4/6. Fs value is 0.58 Fy into AST required divided by AST provided. If you remember, see, whenever the check for deflection is this is called the serviceability criteria. Serviceability criteria is always done on the almost on a service load. So that is why this 0.58 Fy is, you reduce the yield strength to almost to the half. That is done in working stress method. Okay, in working stress method, the stress is reduced to almost to half. That is why this is a check for deflection is also called serviceability check. And serviceability check is always done for the service load. So that is why this yield stress is taken as only 0.58 Fy, because in the working stress method, the stress in the steel is reduced almost to the half. Okay, that is why it is 0.58 Fy. So AST required was this one, AST provided was this one. So we are getting 235.84. So in the curve we have 240 curve we have. So close to that you can see. In the percentage of okay, in a C here I want to make one mention. Here for a flanged beam they given one note. Are you all able to see this one? You are able to read this? For flanged beams, the value of A or B modified as per figure 6, and the reinforcement percentage for use in figure 4 and 5 should be based on area of section equal to BF into D. So what you have to do is you have to find out the percentage of steel. Percentage of steel will finding out 100. AST provided was 1140 divided by BF is 1933 into D is 400. One of you please quickly calculate and let me know. This 400 will become 4. So 1140 divided by 1933 into 4, how much you tell me? How much percentage steel?
0.147.
14.7%.
147. This is correct? Okay. So now I will show you the graph. I will draw a graph here. Now where it is cutting in 240, this is the 240 line. This is a 240 line. It is cutting somewhere here, right? It is cutting somewhere here in a 240 curve. So your modification factor is almost 2, or you can take 1 point. This is 1.8. So more than 1.9 is the modification factor. Is that clear, everyone? Modification factor. So 0.14 line, if you take it on 240, it is coming out to be 1.8 or 1.9 or something like that. Okay. So if you go here, I have taken this. Okay. So that's what I have done here. 1140 into 100, 1933, 0.147%. Now from figure 4, beta value is equal to 2, because for 240 it was coming out to 1.9. For 235 it will be, more than 2. For see here, this is This is and all 240 line. 235 is more than 2. So 2, you can take 2 also. That is why we have taken beta value as 2. Okay. Now if you check modification factor for the flanged beam, this also you have to check here. Modification factor for a flanged beam here in the next figure. So if you see here, ratio of web width to flange width. What is your web width? 300 mm. Flange width is 1933. Find out what is the ratio. 300 by 1933. It is 1 by 6 point something on how much?
0.155.
0.32.
0.132, right? So from 0 to till about 0.3, the reduction factor is 0.3, 0.8, right? 0.8. Here you see, this is the line. From 0 till 0.3, this is a straight line. So that reduction factor is 0.8. Okay. So that is for BW by BF 300 by 1933, 0.155. From figure 6, zeta is equal to 0.8. Now you already found out everything. So L effective by D provided is 5300 by 413.25. Now right side value, allowable, maximum allowable deflection value is 20 is the basic value, alpha is 1. For example, let us say if your beam is of 15 meter length, then what we will do is the alpha will become 20 into 10 divided by 15. Okay, it is given in B, section B in the code. You see here I have explained this before also, but here for span about 10 meter, the value in A may be multiplied by 10 by span in meters. Okay, so that's what here. So if we have beam span is 15 meters, then it will be this factor will not be 1, it will be 10 by 15 will be the factor. Okay, but right now we have only 5 point something, so we can that is for 1, and this is for a tensile steel, this is for a compression steel, this is for a flange. This is coming out to be total is coming out to be 32. Obviously 13.825 is less than 32, that is here. So your check for deflection is okay. Okay. Finally, you will have a detailing of reinforcements, that is this one. This you should end with this one. Okay. And this is only cross section. Longitudinal section will I will tell you in the next one. Okay. So you will get the question like this only. Now tell me, you have any doubt or not? Is there any doubt? Anybody in any of these things? Mostly people make mistakes in load calculation alone. But load calculation is very simple if you understand, if you are able to visualize the actual slab, actual beam, where it is, how we are considering only 1 meter width, everything. If you understand it systematically, you will not have any problem. Okay. So if you have any doubt, you let me know. Otherwise, 1 second. So we have started with this one, writing all the given data. Then to find out the cross-sectional dimension, you are taking the help of L by D ratio. Now for the L effective, you are taking the help of clear span plus width of the support. And from that you are finding out what is the value of D, effective depth value. You are assuming the higher value than this one, that is 400 mm. Now assuming the diameter of the bar and stirrups dia and clear cover, although we assumed 20 mm, finally we provided 22 mm. But that will be covered here. See, if you put 22, this will become 11, this will become 449. So we have taken 450 mm, that is fine. So these are the cross-sectional dimension. Once you know these things, you have to find out the width of the web. This should be overall depth is 1.52, 2 times the width. From that you calculate, then find out the BF. Once you've done that, you calculate the load, that is a live load on the slab. self weight of the slab. Self weight is, see, when you calculate the load on the slab, including the floor finish, including the self weight, including the live load, it should be in terms of kilonewton per unit area meter square. So 5 kilonewton per meter square, self weight of slab, then floor finish. I have taken 0.875. If you want, you take 1 kilonewton per meter square. So, but I have to write here. I have to write here because in the problem it's not given. So any value you are assuming, or then you write take floor finish as this, floor finish as 0.87 kilonewton per meter. So total is 9 kilonewton per meter square. And if you see the load transfer from slab to beam, load transfer from slab to the beam, intensity of load UDL multiplied by the center to center of this one beam, that is coming out to be 27. Suppose in some situation you have this kind of situation where one is, this is 3 meter, this is 5 meters. Then how the transfer will happen? How will you take this one? Then you have to take half of 3 is 1.5. Half of 5 is 2.5. So together 1.5 plus 2.5 is, it will become 4. Okay, or you average it, 5 plus 3 divided by 2, that will be 4, like that. Okay, in case of if the center to center distance is not uniform. Okay, so similarly self weight of the web also you have to include. This is the total UDL on the beam, UDL intensity of on the beam is small w. I have marked to a close number, whole number. Then you find out the factored UDL intensity. Then after that you found out the bending moment values. After that everything remains same. You find out, actually you should find out mu w limit and find out whether it is singly or doubly. Then within the flange we are assuming, and everything else is after that everything else is same. Okay, so that is the end of your the second unit. But somebody asked, okay, is there a doubly reinforced T-beam or something like that? Yes, you have doubly reinforced T-beam. For example, if you see, design a T-beam of a width at 750 mm effective width of flange. Depth of flange is 100 mm. This one I am not going to go detail. I am just going to run over the steps and you do it yourself. Width of the web is 200 mm. Total depth of the beam is 550 mm. To develop an ultimate moment of resistance 450 kilonewton meter. M20 grade Fe 415. Effective cover is to the steel is given. Carry out necessary check. Okay. As usual, you will write all the data. Everything is given here. This is what this 550 is what? What is this 550?
Effective depth.
Read properly. Huh?
Overall depth of the beam.
Overall depth. That is what? Capital D, right? So what is given as capital D here. And the effective cover is given here 50, right? So accordingly you have to do it. So first step is whether it is singly or doubly. So first find out the effective depth, D minus effective cover 500 mm. So you know DF by D is how much? DF is 100 mm given. D is you found out to be 500 mm. So DF by D is coming out to be 0.2. If it is coming out to be 0.2, it is you have to take the first case. Therefore, DF will cover the equation. So from this one G 2.2, this is the equation. This is the taken by the web portion alone. This is taken by the flange portion alone. So total mu limit is coming out to be 360 kilonewton meters. 360.75 or 360. It's okay. 360 kilonewton meter. But what you have to design for? You have to design for 450. So obviously, since your mu is greater than mu limit, you have to design as a doubly reinforced section. Okay. So this step is almost same as what you have done before earlier also. So because it is 0.2, the equation will be DF equation. This is given in page number 96. Okay, 96. The last equation is this one. Page number 96 of your code. Now it is doubly reinforced beam. In a doubly reinforced beam, what we'll do? In the tensile steel, there will be two parts, AST1. So how do you find out AST1? So here you see, this is the web portion. This is the in the T. This is a web portion alone. This is the XU max. So this is a D minus 0.42 XU max. Okay. So if this is AST limit or AST1 0.87 FY AST limit or AST1. So your how will you find out if you take a moment about this point? You can write 0.87 Fy into AST limit into D minus 0.42 XC limit is equal to, that will be MUW limit. That is what this one. So MW limit divided by 0.87 Fy D minus 0.40 XC max. This is for this portion. Okay. Now you also have this portion. Here, this is the moment taken. This is the flange. Flange is 0.45 FCK BF minus BW into DF is the compressive force. At the bottom, you have 0.87 Fy into AST. So we are taking moment about this point. So that is a moment about flange is equal to 0.87 Fy AST, whatever the AST here was. With this AST limit, here there is, let us say, some AST itself. So 0.87 Fy into AST D minus DF by 2. This is the lever arm distance. That is this. Okay. So you are finding out what is the AST required for this one. You are finding out what is the AST required this one. You add these things together. That is AST1. So for that, so MW limit is 138. This we already found out in the previous step. In the previous step, there are two portions. MUW limit has two portions. One is for the this one. That is 0.138 FCK BD square and all. Plus second one is for this portion. So this portion alone is 138 into 10 power 6. So correspondingly, D minus 0.40 XC max is the lever arm. So 0.87 Fy D minus 0.42 XC max is the lever arm. That is one. And this one, second one is for the flange, and the lever arm is D minus DF by 2. So that moment is already given in the previous problem, previous step, 0.87 Fy D minus DF by 2. If you calculate, this is coming with 2330 millimeter square. This is only, see, together this is 138, this is 222. It has taken only 360 kilonewton meter total right now. So you have some extra, that is AST2. So AST2 should be designed for 0.87 Fy AST2 into D minus D dash should be equal to MU minus MUR limit. Total MU was 450, MUR limit is 360. So remaining 90 kilonewton meter you have to provide AST2. So that is this one. And the lever arm is D minus D dash. This and all we discussed in doubly reinforced beam. So AST2 is 554 millimeter square. Now if you add this AST1 and AST2, you will get total tension steel is AST is equal to AST1 plus AST2, 2330 plus 554, 2884 millimeter square. So if you are providing 28 mm diameter bars, 28884 divided by 615, it is coming out to be 4.7. So you have to provide 5 numbers of 28 mm diameter. So providing 5 into 615, 3075 you are providing. Okay. So this is a tensile steel. So you have compression steel also. Again, we are taking the help of the equation given in your code. 0.87 Fy AST2 is equal to Fs into ASC. But Fs, how will you find out? This and all, the procedure is already given here, which you already know, which we have discussed while discussing doubly reinforced beam. Here, this is the formula. How will you find out Fsc is mentioned here. You find the strain values. So first we find out epsilon SC. Epsilon SC is 0.0035 1 minus D dash by XC max. So for that, if you substitute, you are getting 0.00277. Now from the graph or from the table, you find out epsilon FSC. FSC is coming out to be 352 Newton per millimeter square. Right? You have this kind of graph which I have given in the material. Like this graph will be there, right? Or from table also you take table 6.2 or something like that in the PT. So for this train, you find out what is the stress value that is coming out to be 352. So now this is known, Fy is known, AST2 is known, FSE known. Only unknown is ASC. So ASC you can easily find out. ASC coming out to be 568 millimeter square. So providing 16 mm diameter bars, 568 divided by 201, it is coming out 2.82. So you have to provide 3 number of compression steel of diameter 16 mm. So ASC provided is 3 number of 201 603 millimeter square. So a minimum you will not check because we are providing doubly reinforcement. AST minimum check is not required, but AST maximum you have to check. So 0.04 PWD is coming out to be 4,400. We have provided only 2,334 or 834 from previous step you can see. Similarly, ASC maximum is 4,400, which is greater than 603 that we have provided. So this is also fine. Now detailing of reinforcement is this one. We have provided 5 number of 28 mm diameter bar at the bottom, and we are providing 3 number of 16 mm bar at a compression steel. Remember, when you provide the reinforcement compression steel, it will be in the top. This in the here. It should not be here. This is not the beam is not ending here. Beam will be up. Beam is considered up to here. Okay, that is why then only there will be a perfect bond between the slab and the beam. Okay, so don't think that you have to provide the compression steel only here. That is completely wrong. Your compression steel should be in the topmost area. So this is 3 number of 16 mm diameter bars. So and of course you have to check for spacing of bars need to be done as we did in the previous problem. Okay.